Probably one of the most controversial statement in mathematics, all natural numbers summing up and giving minus 1/12. Quite absurd one, but an extremely important one. We're going to discuss about it and reveal the truth behind it in this video. Starting by stating this series, Sir Srinivasa Ramanujan, one of the finest mathematicians ever, had addressed a long letter to Mr. G.H. Hardy, and this is a portion of it, stating, I've got theorems on divergent series, theorems to calculate the convergent values corresponding to the divergent series. In this video, we'll be talking about this series. Also, this series is significant. In the original paper, we can clearly get a glimpse of his work. Over here, let's talk about it. Starting with the first proof, it will look quite similar to the work that was shown in the previous slide. Considering the series S1 as 1 minus 1 plus 1 minus 1 plus 1 minus 1 and so on. Well, considering it to be a geometric series, we can apply the formula for the infinite GP series to get 1/2. Well, it's not true, because we have taken R as the common ratio as -1, but we are not allowed to do so. But let's keep that aside and move on. Let's consider a second series S2, and I've already mentioned that this series is significant. Well, this is simply the square of the S1 sum giving 1/4. This can be seen if we make a table and write all the corresponding values as we multiply every term of the series with each other. Well, the table clearly has infinite rows and columns. Well, this is the final series and the most important series S3. Multiplying 4 with S3 and putting each term under each even term of S3, and by subtracting it, we get a particular expression. Well, this sum is looking friendly. We have seen it somewhere. Yes, it is S2, which is 1/4, and we finally get minus 1/12. Well, it's not a strong proof, as we have manipulated infinite series like the finite ones. Also, the common ratio factor, as I had already mentioned earlier, is also wrong. But this is not the only proof. Coming to the second proof, we all know that the general form of the zeta function is this one. Clearly plugging in -1 in it gives us the required summation. Bernard Riemann, while proving a functional equation, gave this identity. Substituting -1, we get bingo, minus 1/12. In case you are unable to understand how these values out of nowhere came on earth, I will talk about it in the description below. Well, this is again wrong. The identity of zeta function is valid for real part of s greater than 1, but we are plugging in -1. But we are still not done yet. The third proof is a proof on which Ramanujan and G.H. Hardy worked and was officially Ramanujan's second proof. Here we'll be stating the Euler-Maclaurin summation, which looks like this. Wow, so beautiful. The capital B over here represents the Bernoulli's number and P is a prime. Ramanujan took prime approaching infinity and framed the following sum. The constant C over here is specific for particular series. After that, taking R approaching 0 as x approaches infinity, we get this expression, and we get to see that in a general case for f of x with no divergence at x equals 0, we get this following expression. Well, we get this expression by comparing both of the initial summations that I have already mentioned. Well, this C can be used in finding the sum of the divergent series by plugging A equals to 0. Now, the second Bernoulli's number is 1/6, and by taking f of x equals x, as it is the function we need, we get the constant as minus 1/12. This is the second proof given by Ramanujan and has its own significance. Well, Ramanujan was a true genius, and there must be some reason why the previous proofs were not compatible with this statement. If we have a close look on what he had written, we can clearly see that he had stated that these are undoubtedly divergent series, and these values are convergent values corresponding to the divergent sum. Never did he mention that these sums are convergent. He assigned some convergent values to them, probably because he knew its significance. As there are numerous applications of this sum, as in bosonic string theory and also in Casimir force calculation for a scalar field in one dimension.